All right. Hi, everybody out there in the community. How are you doing? I hope some of you were able to catch Cecilia's stream. I hope it was great. I had to prep for this stream, but I'm sure it was an awesome workshop. I loved Matplotlib. It's one of my favorite libraries. I use it all the time to make figures for papers and things like that. But yeah, maybe someone in the comments just tell me hello or say hi or something so that we know that we're ready to go. All right, so why don't we then begin? I'm just going to give a brief recap while we're waiting for some folks to say hello. Hi there, 404. Thanks for the audio video check. Really appreciate it. And while we wait for some folks, I'm just going to go back over a few of the things that we discussed in our original stream today, this morning. So hopefully you can see this. And so welcome for the stream. And if any of you were not here in the previous stream, it'd be great to hear from you. If you wanted to introduce yourself, give some kind of first name or greeting, tell us what country you're logging on from today, if you want to share that information. And then what would you like to learn today? But I'll just tell you a little bit about the goals here. We're working on trying to actually get an LLM working on our computer, one that we program ourselves. And it's not going to be anything revolutionary in terms of it's not going to be ChatGPT 5, but it's going to give us that firm grounding in what is transformer, what is LLM, what we want, right? And we have a big agenda. And the first thing that we really did today was we did foundations of language models, and we set up the environment. And we even did a little bit of data preparation and tokenization. That was sort of towards the end where we actually discussed embeddings, concepts like embeddings, concepts like tokenization. And then today, I think we can cover some of these other bullet points, these last three here, which are going to be building this minimal transformer model, okay, training, evaluating, and fine-tuning that. And then we can wrap up and have a Q&A, and maybe I'll challenge you all at that point to go further with this project and give you some ideas on how you could go further. All right, but just to give you some expectations, questions are definitely welcome, and any participation is encouraged. Really love to hear from you all. And the GitHub will be shared as well. So, and by the way, I'm sorry, GitHub, I don't know why I wrote that there. I meant to say the Colab notebook. So let me actually share that with all of you in the chat, because, yeah, you might not have access to that. You might have missed the first workshop, but there's that Colab link. And by the way, since I forgot to share, since we're on the topic of sharing links, I'm going to send you some more links. The second link I just sent is the link to check in. So that's super important, okay, for us to get you that. And the third link that I sent, which I just sent now, is a Google Drive link, which is the link to the slides. And so you can actually use those slides to follow along with what we have planned today. It's going to be those slides plus a little bit of coding. Okay, so now you have a way to follow along with the slides and you have a way to follow along with the coding. All right, so we already went through this portion. So I'm going to go back to our notebook where we can check that out. Let's see. Use my own link. And yeah, this was our workshop. So we talked about probabilities. We talked about joint probabilities. And that was the first thing we did. If you're not familiar with this, it's what they call the chain rule, because you're really chaining probabilities together. And so we know, for example, that these words we're looking at are hello, world, and again. And I'm going to assign probabilities to the possibility that these words will appear in a sentence. So the first probability was 50% that hello would appear. And then some new word, now that hello has already appeared, world could have a 30% chance of appearing. And then we have finally probability of word 3, which is again. Hello, world, again. And that would be 0.2. All right. And so that is a good thing. And then, by the way, I forgot to mention this last piece here, but I did add some default probability so that if the word is not found in the library, that's okay. Oh, okay. The collab said access denied. Thank you for reporting that, Marie. And okay, Atanshu. Hi there. Good to meet you. And awesome to have you logging in from India. Everyone, we have a really global community here in Global Hack Week, if you're new to that, and that's what makes it so special. Us live streaming, we can get people from all around the world. So this morning, we had some folks logging in from India, from Brazil, from all over the US. So it's really great to see you and welcome. And okay, one more thing. Let me try and fix this Colab notebook so that I can share it appropriately. Okay, it says maybe I copied the wrong Colab notebook. Let's try this again. Can you all try this link one more time and see if you get access? But while we're waiting for that, I just wanted to show you all the chain rule here. So we have these 3 probabilities now, and we get the probability of a sentence like hello world again by multiplying them. So we multiply hello by this probability, by this conditional probability, and we get 0.005. So there's a very low chance that all of these will happen together as they do. But it has been known to happen. So we can say that the probability is low, but that it's realistic. And these transformer models are essentially computing these probabilities based on their training data. And thank you, Marie and Guacol, for confirming that the slides are now, or the notebook is now available. And yeah, just if you're looking at this notebook now for the first time, you might be wondering what this stuff is, and that's why I'm going through it right now. This is stuff we did in our first workshop today. And so the second thing in here is this transformers library. So this is the Hugging Face Transformers library. And to install, you simply use this !pip install transformers. And it should install all of the required dependencies and codes as you see there. And then this library here from transformers import, we can get a module called auto tokenizer. Okay. And so this is just a really good way to take sentences and convert them into tokens. All right. So here's our tokenizer now. And we're going to use the BERT base uncased. So uncased meaning that there's no case, and you'll see how that works out actually. And BERT is a large language model produced by Google Research. So we have a sample text: the quick brown fox jumps over the lazy dog, and then we just use the tokenize method. And when we run this, we get our sentences broken down into tokens. So now you can see the, quick, brown, and so on. And each of these tokens has a unique ID. So you can see the is 1996. Jumps, let's see, which one is that? 14523, right? All right. Hopefully the audio is back now. Can anyone hear me? Okay, great. Sorry about that, everybody. I had to change microphones. Not sure what happened to my other mic, but sorry about that. And then someone else said my video is a little bit choppy. Sorry about that. Yeah, I'm working in a new apartment now. I think I mentioned that during the Today in Global Hack Week stream. So let me do my speed test actually. Yeah, it's definitely not great. I'll have to fix that and work on that. But video is better too. Great. Yeah, the speed test is actually saying that the internet connection is not bad. So I'll have to still look into that. But all right, so let's keep going with this, and we can continue on to embedding dimension. So embedding dimension is the vector representation of tokens that encaptures their semantic meanings. So you see that there's numbers associated with these tokens, right? And we can calculate the embedding dimension, or we can calculate the embedding of some vocabulary of tokens. And we use an embedding dimension of, in this case, 64. So if we looked at this, we'll just run this. if we were to look at the embeddings dot shape, you can see it's 4 by 64. Okay. And so we're getting, we have 4 tokens that we gave as an example, 5, 10, 15, and 25. And we are getting 64 different relationships between these words, a single word in the sentence, and all of the other words in this vocabulary, this 1,000 tokens. And so the embedding layer is helping us form vectors for each token that captures what that word means. Okay. So then we talked a little bit about context, and we discussed those concepts a little bit, but this was all the code we wrote. So if you're joining new for this workshop, you didn't miss that much code. It was mostly just explaining about these concepts, and we did a little history of natural language processing field, or NLP, as well. But today we're going to actually be diving in a little more into the transformer architecture. Okay, so you can see that over here. And one really important attribute of the transformer mechanism is self-attention. And this is what we're talking about when we're talking about the difference between transformer and, say, a 2 gram or 3 gram model. Because in the 2 or 3 gram model, we were saying, okay, you know what's important to predicting this word? The previous 2 words or the previous 3 words. Now with self-attention, we're saying that everything could be potentially in the input sequence could potentially be relevant. And you, as the model, will decide which parts are most important, and that can change based on which word you're looking at. Okay? So we're going to do a simplified self-attention case in PyTorch. I think you may remember we talked about the fact that you will need to have PyTorch downloaded for this workshop. So let's go ahead and look at that right now. But before we do, I had a request of how does it look in a chart? How does the embedding look in a chart? Let's take a look at that, actually. I'm not sure. So it's a tensor with shape 4 and size 64. So what I think would be best to do is we can try to use Gemini, I think, and try to create a heat map representation of the embeddings. I think that will be a really good way to visualize the embeddings. Hopefully we can get it running. All right, so I guess we just need to fix this one thing. All right, so I'm not sure I like this. This is just generating a random projection matrix. Okay, that's not exactly what I wanted. Why don't we just make a heat map of the embeddings themselves? Okay, this is much more like what I wanted. So that just goes to show you can't always trust these AI models to get everything for you. You kind of have to get it yourself sometimes. So you can see the similarity scores, these projection scores, which are just telling, with word 0, for example, which was the 5 token. You can see which of the 64 embedding dimensions it's most similar to. So there's this one that really stands out, number 60. And then there's some that it's just like totally opposite to, like this number 4. And each word has this rich context of how it relates to all of these dimensions. So yeah, it's really good to check into that stuff. Thanks for suggesting that, Threeville 1987. Okay, let's go back to our self-attention mechanism though, because I just want to refresh you before we go into a new code. We're going to be looking at this very similar concept, but in PyTorch. And so, yeah, let's go ahead and import Torch again. I think we imported Torch already in this live workshop. Yeah, you remember before we imported Torch and torch.nn as nn. I'm going to re-import those, and I'm going to re-import .nnn as the .functional model, okay? And what that means is that there's a series of functions, optimizing functions, that are contained within the NNN module, submodules, if you will. And F will let us access those, okay? And so then I want to import math as well, all right? All right, so first I'm going to make the self-attention, head here, and we'll make a method called self-attention. And there's going to be 3 arguments that we put into here, okay? So there will be Q, which is the query, K, which is the key, and V, which is the value tensors, okay? So all of these are tensors, objects. And they're all going to be like, we're going to use operators to manipulate them. And what we'll do is multiply the token embeddings by some learned weight matrices, okay? So basically, we're going to compute these 3 different vectors for every single token, and then calculate the similarity between them. And we're going to use an equation called softmax to do this, all right? So first, I want to make d underscore k, and this is just a way to diagonalize this, I guess. And then we're going to compute the dot products between queries and keys. Compute the dot products between queries and keys. All right. And so these are our scores. MATMUL stands for matrix multiplication. All right. And so this equation that I just wrote down is the dimension of the key vector. Sorry, dk is actually the dimension. I'll write that. I'll write that. And this function here is what we are trying to apply softmax to, which is our optimization algorithm here. And so let's say that apply softmax to this quantity. And we'll use attn f.softmax scores dim equals -1. And so this is the attention, right? How do I know this? Well, think about what we're doing here. We're doing a matrix multiplication. a dot product between the queries and the keys. And then we are going to use softmax, which is going to be the way that we compute attention. Okay. So we did that, and now we're going to find the output, which is the final result of this self-attention, where we multiply the weights by the values themselves. Okay, so we just take this matrix multiplication and we do it attention multiplied by V. And as an output, we'll just return output, all right? And so you'll see how this works. I actually want to put some print statements here because I want to show this, all right? Q and V. And then we'll print DK as well. So I'll just call these query key and value. And then I'll call this dimension. This is scores, attention, output. So we can see the whole process here. And I'm going to create a dummy query key value tensor. All right. So we'll do some batch size 1, sequence length, let's say 5, we'll give that. And we'll do key dimension of 64. All right, so here we're going to just, this is what the embedding is doing on its own, but we're just going to use random values for these query key and value pairs. And the output, we'll use self-attention, Q, K, and V. All right. And then I guess in the end, we'll print, I want to print output also. All right. Okay, so here's what we have here. Lots of output. So first is the query tensor. All right, so these are just random values. And here's the key tensor. And here's the value tensor. All right. And to compute the score tensor, we just did a matrix multiplication of Q and K. So we took the query tensor, which looks like this, and we just multiplied that by the keys. And you can even see that first row, the multiplication of those two. Now, in addition, we did an attention tensor. What's the difference between the score tensor and the attention tensor? Using this softmax function, all right? And let me show you how this soft function works. Converts a vector k of real numbers into some probability distribution of k possible outcomes, all right? And so we're just going to take the output of a network, which are these scores for each relationship, right? When we multiply the query and the key, and we're going to convert them into probabilities. All right. And so that is basically what the self-attention mechanism is doing. Now, as far as multi-head attention goes, that is when we run several self-attention mechanisms in parallel to capture diverse aspects of the input. So let's take a look at a conceptual snippet of code so we can see how that works. So now we have a self-attention module. I'm going to remove some of these print statements because I just liked to have them for the purposes of the demonstration. But yeah, we're going to definitely remove those so we don't get a million things happening at once. Yeah, so again, this self-attention output is a tensor of size 1, comma 5, comma 64, right? And that's because there's one batch, 5 elements in the sequence, and 64 is our embedding dimension. But let's check out the multi-head attention now. So we're going to define a class called multi-head attention. And we're going to first give it a constructor method. And so a constructor method, if you're not familiar with that, this is where we use a double underscore. It's also called the Dunder method because it's a double underscore to tell the program what codes need to run when there's a new object created. So when a new multi-head attention is created, we're going to give it these parameters: self, which is just the object itself, the dimension of the model, and the number of heads. All right. And so we're going to do super multi-head attention, which just gives us what we want there. And note that we want to assert, this is actually exactly what I wanted to write next, which is that the dimension of the model has to be divisible by the number of the heads. Why do I say that? Because we're going to distribute the model attention over the whole entire, just over the whole span of this model. And it needs to go in evenly, or else one of the heads will not have the same exact matrix shape as the others. So they all need to have the same matrix shape so that the algorithm can run appropriately. And you'll see that in a minute. So we're going to start defining some attributes for this multi-head attention. One of them is going to be dk. So this is, remember, the value of those key pairs. And we're gonna say that the dimension of the key pairs is just the dimension of the model divided evenly into the number of heads. So we don't have to use this double division, actually, because we just asserted that it must be divisible by the number of heads. But regardless, we'll just use it here for best practices. And then we want another attribute, which is self.numHeads. It's just the number of different heads. And now we're going to create linear layers for the value, query, key, and values. All right. And so let's start with linear queue. So this is the linear layer for the queue, the queries. And for those of you who don't know what a linear layer is, it's basically one of the most simple connective layers in the neural network. And you're just having some input that you connect to some output, and they can be multidimensional. So that's sort of the key there. And we're going to do this for every single one of these queries, keys, and values. Create a linear layer with a dimension of d underscore model by d underscore model. And then here's the linear out we're going to do as well. So we're going to use a linear layer as some output as well. All right. And we want to also create a feed forward method, because right now, as it stands, the multi-head attention, excuse me, it's just a bunch of empty linear layers. So we want to actually feed the data forward using linear projections and then calculating attention and so on, just like we did with the self-attention module, right? So let's go ahead and do that. We have define forward, and we're going to use that same self, and I'm just going to use x, some x, all right, which is going to be the input to this, and it's going to have three things, okay? It's going to have batch size, sequence length, and d_model. All right. So those will be the three dimensions. Now remember, if you look back to the output.shape, those were the same exact dimensions of our self-attention. So we're just going to use those same exact dimensions for the multi-head attention object. And so linear projections is the first thing we're going to do. And we're going to use Q so see how we pass X, which is the attention, the self-attention output, similar to the self-attention output, into this linear layer, Q. And then we do the same for each of the others, keys and values. And we're going to split this into multiple heads. All right. And so this is the different step here from the previous situation. And so we can do Q. Let's write that actually, split into multiple heads. You can write Q equals Q.view, batch size, sequence length, self.num heads, self.dk, dot transpose 1 and 2. So we're going to look at this Q, and we're going to transpose into a 1 by 2. And then we're going to do the same for K. And the same for V. All right. And so we're going to then use the attention output, which will be using that same self-attention function. So we just go attention output, self-attention, Q, K, and V. And finally, we concatenate the heads and put everything through that final linear layer. So we split into multiple heads here, right? Q, K, and V. And we computed the attention for each head. And then we put through the final linear layer in the end. All right, so let's go ahead and discuss that here, or go through that. All right, so now we have an output of the feed forward method. So we have D equals 128, D underscore model, that's the model dimension. The number of heads, which is 8. The sample input, which is essentially the torch.random. We'll just make some random sample input, but this is essentially what you would be giving in this random, or these inputs, which would have some sequences, some dimension, embedding dimension. And we're going to define a multi-head attention using this information. And so when we pass the sample input, which is, again, having a batch size of 1, sequence of 10, and dimension of d underscore model, or 128, when we pass that into as an argument into multi-head attention, what happens is it's going to use this and pass it through and compute the attention scores on multiple heads and give us an output. And you can see we get an output 1, 10, 128. And so you can see what the actual, this being done multiple times along these dimensions is actually going to do. All right, so that's the basic concept behind the multi-head attention. Let's see if we can show a little bit of thinking behind this. Someone asked, what just happened at the end there? This is where the attention calculation happens at the end. And so if you remember, we used this self-attention here. We defined this already as that softmax function, right? And so we're computing that attention. The key difference here, though, is that you actually concatenate the heads. And so concatenating the heads is something that is happening at the end, where, remember, all of those heads are looking at different parts of the sequence in parallel. It's going to really help the model cover the whole length of the sequence, or of the data rather, and get that information. You can see this tensor transpose that shows you that, right? So how many heads are we using in this case? Does anybody want to take a guess here? How many heads are we using? That's right. So we're using 8 heads, right? But remember, initially, the attention has an output of batch size, num heads, sequence length, and d underscore k. So with transpose, we are taking the number heads and sequence length and swapping them. You can see we're swapping 1 and 2. So we're going to be able to then concatenate along this num heads dimension, along those 8. All right, so good questions. And now let's go ahead and move on to the next portion here, which is what we call positional encoding. And so Multi-head attention, we looked at a conceptual snippet of, okay, how do we compute the attention score? We use this softmax function that converts things into probabilities, these weights of tokens and their semantic embeddings. We compute probability distributions using softmax function. Then we looked at multi-head attention, which is where we had 8 different heads, or any arbitrary number of heads. They just need to fit within the data and or the dimension of the data, and then computed self-attention on each one, and then contiguously bound them together in the end to get our attention output. But now let's talk about positional encoding. Since transformers process these tokens in parallel, how will they know how they relate to each other? And that's where positional encodings come in to play. So this is telling the model about the order of the tokens, not just that we have a bunch of tokens and we're computing their weights among each other, but we're actually going to now look at how they relate to one another. Oh, sorry, that's getting a little ahead of myself there. So let's now talk about the positional encoding part. So we're going to import math and import torch. We don't have to keep doing this, but just the Jupyter Notebook, sometimes I want to run one cell and not the other, so it's better. And so unlike recurrent neural networks, there's no sequential nature to this. The input sequences are essentially just bags of words that we calculate attention between. So to get some positional encoding, we're going to add a vector to each word embedding that will tell us about its position in the sequence. All right. So first, let's define this positional encoding method. And we're going to use an argument called sequence length, which is just the length of that sequence, and the dimension of the model. All right. And so let's go ahead and pass this in. We're going to use PE equals the positional encodings. So we'll just call this a matrix of the positional encodings. For now, let's just call it some zeros matrix. And it will have dimension of sequence length and D model, okay? And so this code is going to iterate through each position in the sequence and each dimension of the embedding. So we're going to use a nested for loop. So we'll use position in range of sequence length for I in range of 0, D model, and 2. And then we're going to use a sine function. Why do we use a sine function? Has anyone here heard of something called cosine similarity? Yeah, so in cosine similarity, why do we use cosines and sines for that type of thing? Yeah, it's used with vector embeddings, right? And so the reason we use this is because we're gonna use for each even dimension a sine function to calculate the positional encoding, and for each odd dimension we'll use a cosine function, and these are even and odd functions, right? So as a result, we can basically learn the positional relationships between the words, and if they're really similar or not, right? So then we'll just go ahead and do the last step here, which is if I plus 1 is less than the D model, we'll use the cosine, all right? So one key thing here, each of these encodings will help us understand the relationship between the different things in the sentence. So let's try this out, actually. We're going to generate positional encodings for 10, a sequence of length 10. So this is 10 tokens, I guess you could just say, and a model dimension of 128. So our model will be 128 in size. And so let's just go ahead and print this out. I'm curious what this looks like. All right, so here's our tensor. And just so we can look at the shape of this tensor, it has a shape of 10 and 28, right? And so 10, remember, was our sequence length, and 128 was our model dimension. And so you can see that, like, for example, the positional encoding for the first one here is 0, right? Remember, sine of 0 is 0, right? And then over here, in this one here, our positional encoding is 1. And remember, cosine of 0 is 1. So we're going to get a bunch of zeros and ones for this first case. And then in the second case, we'll start to break off of that. And the idea is to just assign some sort of positional encoding to each piece of information, so that the model knows that where it comes in the sequence. All right. And so then we're going to do our feed forward. And this is kind of like the meat and potatoes of the transformer model. Okay. So let's go ahead and talk about it. So after the attention layers, you might think, oh, okay, so we have attention layers, right? But so what? That doesn't mean that we necessarily learn about the transformer or enough to make any meaningful output. Well, each token then passes through what we call a feed-forward network. So there's two main concepts. There's residual connections and layer normalization. And so we're going to talk about both of those here. And yeah, let's get into it. So first, let's add a little code to our notebook. And we're going to make a class called feedForward. Very simple. And as an argument to accept this, we're going to use nn.module. And so it could be some, for example, some linear output, some attention output that comes into the model through a linear layer. Remember, the last thing in our multi-head attention module is some linear output layer. So we want to feed this into our feed forward method, and we can do that. So let's start by defining again our dunder method. And we're going to use self dmodel dff. If you're not familiar with the phrase DFF. It's just the dimension of the feed forward model. So the feed forward layer, it's typically larger than D model, and it's also referred to as the hidden dimension. Okay, so the embedding dimension is D underscore model, but the hidden dimension is in the feed forward network. So the reason it's called hidden is because the other parts of the model don't really know about it necessarily, because it'll get expanded in this part and then turned back into the embedding dimension at the end. So yeah, I'll show you how that works, but we'll give it some super class here. And first we'll do some linear layer, which is going to convert from the embedding dimension into the feed forward dimension, which is typically larger, the hidden dimension. And then the next step will be to have the ReLU, and this is layer, and this is really important concept in machine learning. I'm not sure if you've used ReLU before, but it's one of the modules, submodules of NN in PyTorch. And it is basically what we call an activation function. And it introduces some nonlinearity into this linear layer, which allows the model to learn some more complex patterns. So it's not all simply linear transformations. It's actually going to have some nonlinearity. And so otherwise, we wouldn't be able to learn these complex relationships, right, between these words that might not always be really simple linear relationships. Okay. And so then the final thing to do is put a second linear layer, which is going to convert back from our hidden dimension into our embedding dimension. All right, so we've done it now with that. This is the basic idea behind the feed forward method. And yeah, we just took our embedding dimension, our output from our attention mechanism, and we just said, okay, let's add a little bit of nonlinearity into this so that we can learn some complex relationships between the data, and then we converted it back into the old embedding dimension. Okay, so let's say you wanted to use the feed-forward network. That would be pretty straightforward. You could use D underscore model and 128. And let's just say that the dimension of the feed forward or hidden dimension, oh, wow, Google wants us to go to 2048. Okay, sure, why not? But then I'm just going to call our feed forward method, and I'm going to pass in this embedding dimension and hidden dimension. And then the sample output is going to be just feed forward. And remember, we have this multi-head attention output that we defined all the way up here. I'm going to call it MHA output because it's a little bit more specific than just generic output. But yeah, we go over here and we pass that in. And then we will go ahead and continue along with this. So let's check this out, sample output. Oh, ReLU is actually a U here. Sorry about that, capital U. And looks like I'm missing one other thing. I wonder what I'm missing here. Oh, that's right. I'm sorry. I'm missing combining all of these in the forward method. So sorry about that, everyone. So we're going to add some forward method here that just basically takes and returns the actual attention, but operated on by all of these different things. Right, so we actually need to do that too. All right, so you can see the output looks just like the input, same dimensions. The key difference is the multi-head attention is being passed into this higher order hidden dimension and having some non-linearity introduced by the activation function. Okay. And so, yeah, we're making great progress here with our transformer. Let's go ahead and continue. And I'm going to have us install some data sets. And you're going to use pip install data sets to do this. And just while that's running, we'll look at some other things. Yeah, it takes a little bit of time for it to run because it has to download all those data sets. But I wanted to recap for you all what we've done, because it's been a lot of information, I'm sure, to keep in your head and keep straight. So first, we talked about language models and how they predict the probability of word sequences using techniques like the chain rule. And then we talked about this idea of n-gram statistical models and neural network approaches. And these are things we talked about in the first portion of this workshop. But then what we really talked about today was the concepts of tokenization, where the tokens are, text is converted into these discrete tokens. And then the tokens are mapped to numerical vectors, which are called embeddings. And then the embeddings are then further processed using self-attention, using the softmax function into probability distributions to weight the context effectively of these things. And then multi-head attention specifically was used because we would apply several different heads, compute these attentions in that way. And then we talked about positional encoding, which provides sequence order information. So telling the model, where the word came from, instead of just giving it a bunch of words out of order and expecting it to somehow know what that means. And then finally, we talked about supporting layers. So we talked about our feed forward network in particular, which can enhance your model performance sometimes. So we're going to definitely make use of that in the transformers. And I believe, Sandra, the slides, I did share those earlier. I'll share them one more time so that everybody has access. It's the same slides from this morning, this same document. And I guess we are on slide number 32 right now, which is good. We're about halfway through these slides. But I want to ask you a question. How does tokenization affect a model's ability to understand text? Remember, we're converting into numbers. So how is that going to impact the model's ability to understand what is being written here? So if you think back to our code, they have to give each take semantic and meanings with embeddings. Yeah, so exactly. So the token is what determines what part of the sentence has meaning. So think back to the tokenization, the tokenizer that we used in this code. I'll show it actually. We did it all the way at the beginning. The tokenizer is called BERT base uncased. And so in this context, for this tokenizer, the and the are the same. There's no case consideration here. That's not having any semantic meaning, whether you use a capital letter or a lowercase letter. The model doesn't really care. So your tokenizer is taking this text and it's classifying all this stuff. And hopefully it's not losing any meaning for you. There's another aspect to this, which is that you can break down tokenization. So, for example, let me give you an example of subwords tokenization. Let's look at unhappiness, the word unhappiness, okay? And let's look at two separate possibilities. So this is our original word. And possibility one for subword tokenization. We'll use un and happiness. All right, so those are our two words. But here's another possibility. Unhappiness. What do you think of that? So one of these tokenizations is conveying additional meaning beyond unhappiness. The other one is making things more confusing, right? So tokenization is really going to impact your semantic meaning. And then here, it won't understand that write and pencil are closer to each other than write and write. Yeah, that could happen if there is not enough training or actually that could happen if the write and write are assigned to the same token. Yeah. So that's a good point. But if you do training, you can actually teach the model that write and write are have two different meanings. But at the beginning, yeah, it will just know them as two different tokens, unless you define it that way. But all right, that's great. Great job, everybody, with that question. And here's a challenge for you. I want you all to try to modify the code examples, change the sequence length, the embedding dimension, see what that does to your code. I'm going to give you just a minute or two, and we're gonna reconvene, and yeah, just give you a minute or two to play with these and see how they evolve. Okay, I'm gonna go grab a little drink of water while you do that. All right, everybody. Yeah, hopefully that was helpful break for you. For me, it was helpful. I just needed to grab a little drink of water. You have no idea how much you need that if you're going to talk for a long time. But yeah, so just helpful to get a sense of what is all of these things. What is sequence length? What is embedding dimension? What is hidden dimension, for example? And so now we'll talk about what it means to set up the environment. Okay, and this is just setting up your Python environment here. Because we've been dealing with Colab, which is going to give you a lot of this stuff by default, but I don't think it gives you everything that you need. So we have already been looking at Torch, for example, data sets we have used, we have not used yet, I don't think, but I did have you install that because it does take a minute. Torch, TensorFlow, we have used a little bit, and then Sentence Piece and Tokenizers. So these are two other libraries for doing tokenizing and things like that. So I'm going to have you install those, and we're just going to, they should all already now be installed now that you've done the pip install for some of these things. But just so we're all on the same page, we're going to do an import request for them all now. And so we'll do import Torch, import transformers, import data sets. Oh, hang on one second. I just got to get the door. Sorry about that, everybody. I just had to get the door for a minute. But yeah, so there's Torch, transformers, data sets, and tokenizers. That's the last thing I wanted to import here. So it should run. Yeah, and it ran, which is good. That means things are working as they're supposed to. And there's one test you can do on your machine, which is to test if you have CUDA available. And so I'm just going to write a little sentence here, CUDA available, and then I'm going to just say torch.cuda.is available. That's a great way to confirm whether CUDA is on your system or not, right? And so in this case, it says true, or actually, this case it says false. Because if you look at my system, we'll click into it here. It's just a CPU, right? So there's no hardware accelerator, like no GPU, no A100 or anything like that. So yeah, that's good to know. And now let's try and import from transformers, this new module that we just imported for the first time. We're going to import a pre-trained model, okay? But we're just going to do this because we want to confirm everything is working and just reload some pre-trained text generation model. And so this is kind of a cool way we can just right off the bat start doing some stuff with our laptop. Okay. All right. So someone says, I missed the pip install instructions. So let me just put that link back up. Let's see here. I might be sharing the wrong tab too. Sorry, everybody. Okay. All right, so miss the pip install instruction. let me get that for you. So I want you to just do pip install and do it for all of these different libraries just to make sure you have everything. And missed a dataset install script. So here's the dataset install script. You use this in your Jupyter notebook. In your terminal, you could also just type pip install datasets with no exclamation. But in this notebook, you would use an exclamation point at the beginning. All right. So there's that. And then once you have everything installed, we're going to try to just have some sanity check here for the transformers model. So we're going to type from import transformers from transformers, sorry. Import pipeline. And this is just a way to grab some pre-trained model. So I'm just going to call it a generator. And we're gonna have the model be GPT-2, all right, which is kind of an older model. Oh, no problem. Always good to ask questions, folks, because the whole reason we're here is because I want you all to have a good experience and learn a thing or two. And so always ask a question if you want. I'm happy to answer that. But we're just loading a model so that you can see what we're aiming for. GPT-2, you can imagine how old this is if ChatGPT 4 is what we're on now. But I'll show you, it's kind of crazy because GPT-2 was pre-trained on 8 million web pages, and it was not released that long ago. It was released in 2019. And so this is an open source model that we can just access, load up, and use for free. So let's keep going with it. And we already have an idea from Gemini has already suggested something we could ask it. So I guess we will just ask it that. Hello, I'm a language model. Okay, let's see what you say in response. It's loading all of its vocabulary, its tokenizer. Interesting. And I try to be as useful to the reader as possible, but I always try to show and present data. Language model, so it's pretty simple. Now that you've seen our code for an HTTP request. On a science model, I spent a fair little time thinking about which science. Interesting. So, okay, we can see things are working. And this is kind of what we're aiming towards, is some kind of open sourced low code, like low resource model. 8 million web pages sounds like a lot, but clearly it will not get you all the way to modern levels, modern models. But all right, so now that we've done that, we're going to talk a little bit about sourcing and cleaning your data. All right, so you've seen a little bit of what we're aiming towards, and now we'll talk about how we could source and clean that. All right. And so before training a language model, you need text data. All right. So we're going to use Wikitext 2 dataset, which is provided by Hugging Face Library. And I'll just show you what this is. It's 100 million tokens extracted from the set of verified, good, and featured articles on Wikipedia. So we're basically creating a curated list of open source knowledge. Yeah, it's just basically a huge data set to get us. Now, Wikitext 103, that's interesting. I'm not familiar with it, but that would be really cool for us to look at, because it seems like it's composed of full articles, which have a lot of context. So that's sort of ripe for us to look at. So let's keep going with this coding and load in Wikitext 2. So we'll use from datasets, which is where we can get some of this stuff. And we're going to import the module load dataset. So you can import like pre-made stuff. Like, look at this, IMDb. So they have like this IMDb database that you can play with if you want. And I guess it's a couple dozen megabytes. And yeah, they just split that into a bunch of things, I guess, training and testing data. But we're not going to look at that. We're actually going to look at Wikitext. And specifically, Wikitext 2 raw v1. That's the name of it. And so we'll print out the data set. And see, in our system, we're using quite a bit of RAM. So if you're trying this on your laptop, I hope you have at least 8 gigabytes of RAM, I think you would need. But yeah, you can see that there's a lot of text here for us to use. So that tended to work okay. And the problem is sometimes in your models, you might need to clean data sets. Now with Wikitext, as we saw, it's already been removed of, certain special characters, certain punctuations, certain tags, and citation tags too, that might, they might make the data not look great for the training purposes. But in Wikitext, all that's been taken care of for you. But there are some considerations for dirtier data. So you might want to remove HTML tags, lowercase your text if case sensitivity is not something you need to worry about. Because then you can say that the is the same the, whether it's the beginning or the end of your sentence. And then finally, remove and replace special characters. So you could potentially, if you don't have a lot of training examples of some of these strange special characters, you might want to just get rid of them. Yeah, so, okay, I wanted to just show you how regex works. So I'm going to show you an example of that. And you can build your own regex codes and probably ask ChatGPT to help you build those. But I actually just wanted to paste in this regex text I wrote. And you see it says import RE. Let's look at this. And RE stands for regex. Oh, sorry, Guacol wants to scroll up a bit. We can do that for sure. I think it was over up here. Here it is. Yeah. So this is the code for it. I'm going to make this a little bit better for you all to see because that was not very good the way it was formatted before. Yeah, we can pass another one. I wanted to pass another idea for one. Once upon a time in a distant galaxy. Let's try this one too. I think that'd be fun. Who recognizes this? I hope your training data is big enough to recognize this. Upon time, I guess there was a single human being whose name was Kaler Arks. Interesting. What kind of alien thought we have is thought through by the human scientist and upon an ancient age. Interesting. Those are some interesting things. I was going for Star Wars, but GPT-2 had another idea for me. So maybe we'll write a sci-fi novel about Kaler Arks. That'd be kind of cool. But awesome. So this is what I wanted to show you all, was this regex code. And so regex stands for regular expressions, and it's a way to essentially, regularize your input and remove some of this stuff. So first, I have a regex command here, and honestly, these regex commands look kind of strange, and you don't have to memorize them. You can just ask your favorite large language model, hey, what's this regex code for getting rid of a parenthesis or something? But in this first case, we're going to substitute anything with a tag. That's what this is saying, with just empty string. So it's just going to remove every tag. And then the next line is going to lowercase everything. So we're going to make everything into lowercase. And then the final line removes the extra spaces. So if there's multiple spaces, it just replaces them all with a single space. Because, sometimes people will type with 2 spaces after the end of a sentence or something, but you don't want the model to get confused on those things. So once we pass any string into there, like for example, this string here, which you might find in some website somewhere, it will clean it, and let's see what the cleaned output looks like. We'll run this code. There's the cleaned output. So it retains all of the semantic meaning of this, but it gets rid of the distracting features that would not be applicable. So, yeah. Let's see what else we have here. Okay, so the next thing is tokenizing. So we already did a little bit of this morning. We did some tokenizing, but now we're going to actually use this tokenizer on our data. Okay. So if we had some function like we did this morning, I'll just paste what we were doing this morning here first. I think you all remember this if you were there. If you weren't, it's a good review. So we used this transformers library, and we looked at the sentence, the quick brown fox jumps over the lazy dog. And we tokenized the text and even converted them into their corresponding IDs. So you can see that the sentence has been broken up into these elements, these words with individual meaning and assigned token values. And we're going to have some kind of way of handling this stuff. So let's see. Sorry, I just got a little bit lost here in what I was doing. We're going to define a tokenize function, which can do this type of thing for us. And so what this function is going to do is it's going to take some examples, and it's going to return, it's going to first clean. So I want it to first clean. And so we'll do clean texts, and we'll just pass our clean data function to every text that we have in our examples text. So I'm using this text phrase because if you look at our wiki text, that's the feature here in our training data and our testing data and so on. So it's going to take all of those texts and clean them first. Next, tokenize them. So we're going to return tokenizer, and we're going to use cleaned texts. I don't know if I want all these preset things that they have here. Let's use truncation. True is fine, I guess, but padding length, padding, let's use some consistent padding. We'll just do padding true, max length 128, because remember that was those model dimensions. Can't really, we can't really have an input that is larger than our model dimension. And that's essentially what the context window is saying to you. But let's now apply this to our Wikitext dataset. So we can say tokenized dataset, because we have our dataset from before. We have some train category here, remember, of our Wikitext data. And yeah, we can just map this onto our tokenize function. So we'll use batch equals true just to put this in batches. I don't think it's going to take very long, but we can just do that just because it's good practice. And let's run it. All right, we got a little ahead of ourselves because this I used clean text. I didn't use clean data. Let's call it clean data instead of clean text, just to keep everything consistent. And now it's running. You can see it's passing through all of our 36,000 examples here. And it's looking at the, oh, sorry, I wasn't sharing this tab. Here's what we're doing right now. Yeah, it is pretty funny. Sometimes the outputs are pretty funny. But anyway, I wasn't doing anything fancy. I was just taking our regex function that we made and our tokenizer function that we imported and merging them together into something that we can use on all of our data. Okay, and so that's a really good thing for us to do before we start looking at this Wikitext data. Even though it is sort of already cleaned up, we can just do this so that we can handle any kind of text into our model. Okay, and so we did use the map function to apply that to our whole data set, and we tokenized Wikitext. So there were a few things that we did. So we did some padding to make sure that each input sequence in a batch is of the same length. So that means that like every sentence has the same length, even though I have like one sentence that's just hello. All the other words would still be filled in. They would just be empty or like a zero, a token. So that will be really important for making sure that everything is regular and normalized and consistent in its shape. And then creating attention masks. So this is like we would want to know which tokens are actual data and which are just padding, and a splitting data. So we already did the splitting the data based on train, validation, and test. That's already set for us. But I do want to try this data collator with padding thing because I want to go through that. So yeah, we're going to go and try that out because this is an important aspect of it. The primary purpose is to handle dynamic padding because sentences, of course, they're not all the same length, right? So let's import from transformers. Import our data collator with padding. Okay, and so we're going to create the data collator for dynamic padding. Excuse me. And so we're going to create it, and we're going to need to pass some kind of tokenizer in there. And so we'll just use our BERT tokenizer, our BERT uncased tokenizer that we had from before. And let's just select 4 samples as an example from the tokenized data set. Okay. So here it is. This returns a list of dictionaries. So let's just take a look at it first. So it has these 4 features, this data set: text, input IDs, token type IDs, and attention mask. And so let's suppose you only have input IDs, just for an example, and we want to make a list of these input IDs. So let's call that batch dicts. We'll just say, as an example, just have input IDs, just so we can sort of learn on this base case here. So we have these input IDs. And so if we look at this first, oh, sorry, I forgot to, I'll just call it batch input IDs. So if we look at this batch dictionaries, you can see all of these batch dictionaries. And when we use the data collator, it should give us padded batch. Yeah. So now we are seeing that when the sentence is done or completed, there's still padding at the end, so that all of these sentences are the same size. And the attention mask will tell us which ones are filled and which ones are not as well. So yeah, that's just a little bit of a tutorial on that. But let's go back to our slides, because I want to recap what we've done so far. And I think we'll save the final part, which is of creating our laptop models. I think we'll save that final part for the next time, because I don't want to necessarily get into that with the amount of time that we have left. And I know that the next workshop is coming up, which is with Carrie, which is Build Your First AI-Powered Mobile App. So let me put that up on the screen. And I'm going to put the check-in link as well. And this starts in just about an hour from now. And with Carrie, you are going to build an app together. So that'll be really fun. But we're going to be back in just a few hours with the final part of this workshop. So I think it'll be better for us to wait for that. And yeah, but if you want, we'll just recap. So we are going to use the Wikitext2 data set from Hugging Face as our training for our transformer model. And we did some data cleaning and defined some simple cleaning function to remove HTML tags, extra white space. We really prepped our data set for training. And then tokenization, we tokenized Wikitext, and then we prepared everything by using padding and attention masks to tell the model what to pay attention to, what not to. And we used a data collator to automate these tasks. So that's the idea behind what we've done. But yeah, thank you all for joining. And let me tell you when the next one of this series is happening. I'll send you the link for that as well. It's going to be at 9 p.m. Eastern time. And here's the event list. So this is part 2 of the of this, or part 3, I guess, of this series. So all right, take care, everybody. Until next time.